So we can write a recursive function in Mo that will run forever, but does that mean that all recursive functions can run in Mo without running out of space? And the answer is going to be no. So consider this example, where we have a function f that calls itself, but each time it calls itself, it also adds 1 to the result. What happens when we perform substitution here? This function goes in for f and f applied to f, so we get this function applied to itself pattern. Now we have a function and an argument, so this argument will go in for each of these two f's, and that's what we have there. It used to be f applied to f, now it's this function applied to itself, but this 1 plus got added to the outside. And as we keep performing these substitutions, we will keep building up more and more 1 pluses on the outside. And in fact, when you run this Mo program, you will eventually run out of memory. You'll run out of places to store the 1 pluses, which correspond to 1 plus dot continuations, which correspond to do plus k records that we keep building up. How do we know which functions that always call themselves will run forever and which ones will run out of space? We've been talking about Mo, but we can also have the same discussion about Shplait because Mo is meant to imitate what Shplait does here. And as the name suggests for this example Shplait function, the forever function will run forever when you call it. It will not run out of space. You can see that some work is done every time you call the forever function. It toggles x between true and false. But the key point here is that forever is in a position so that its result is the result of the enclosing body. That is, it's in a tail call, tail meaning as soon as you get an answer for this function call, that is the answer for the enclosing function call. So that's why forever will run. We don't have extra stuff that we're accumulating on the outside of the forever call. On the other hand, as this variant suggests, we will run out of memory here. And that's because this call to run out of memory is not in tail position. Because after we get an answer back from that function call, we still need to negate it to get an answer for the enclosing function call. So you can tell which one of these simple functions will run out of memory or not based on whether the self call is a tail call or not. How about this version, which again the name suggests will run forever? You can see that forever now is nested under an if expression, but once we get to this then case forever call, and we get an answer for that, that is the answer for the if, and it is the answer for the function body. So again, there's no more work that needs to be done once we select this branch or select this branch. This function will run forever. In other words, the branches of an if are in tail position with respect to an if, and if the if is in tail position with respect to its enclosing body, then these are tail calls. On the other hand, if I just have true and false in the branches, but the test position is where my recursive call is, that position is not a tail call. Right? That's because once we get an answer for this function, then we pick between the true and false cases. We have more work to do when we get that result. So this position, again, is not a tail position with respect to if. So when we specify a language, we can say which positions of which syntactic forms are in tail position, and from that you can reason about which function calls will be tail calls and not extend the continuation. The implementation of our Mo interpreter with interp and continue in lambda k relies on this specification of Shplait about which things are in tail position. In particular, interp calls continue only as a tail call, which means that when interp calls continue, it is not extending the Shplait level representation. The Shplait program is not going to run out of memory because of that call to continue. The same is true when continue calls interp. It always does so in tail position as a tail call within the continue body. And continue calls continue only as a tail call, and interp calls interp as a tail call, because those functions sometimes call themselves. The only other recursive function that we have in lambda k is lookup, and it too calls itself only as a tail call. So there are no other recursive functions, and that means that the Shplait level continuation is always small, and so the only thing that could possibly grow is the Mo level continuation or expressions or values. Right? That means that our Shplait implementation is not interfering with Mo's memory use. And to make sure that the Mo interpreter with interp and continue stay working right, you must always maintain this property, that interp is only used in tail position and continue is only used in tail position as you modify the interpreter for homework. In fact, following those rules not only makes sure that Mo has the proper space behavior, it turns out that interp and continue just aren't going to work right unless you follow these rules. So again, make sure as you change things in the homework that you only call interp and continue in tail positions.